answer. We can hear. Hoorah. Okay, that's all I need out of y'all. Go back to sleep. Okay, now let me see if I can see this. All right, I can. That is a webwork problem that looks like 8 to the n divided by 3 to the n minus 1. It's a little bit hard to see. Eight to the n divided by 3 to the n minus 1. Okay, so I would use the test for divergence. The limit's not going to be 0, the limit is going to be infinity because the top grows faster than the bottom. The limit is not 0. So I know this thing diverges, but that's not one of our choices. We're asked to choose from the comparison test, the limit comparison test, the alternating series test, or the integral test. Were there any more choices? Or the ratio test. So it's not an alternating series, it's a positive term series. So I can't use that. The ratio test works, sir?
I was just gonna, never mind.
Oh, okay. The ratio test works well if I have products, factorials, and n powers. Well, I have the n powers, but this thing keeps me away from a product. Not going to get many things to cancel. My ratio test is going to give me a 1, and I can kind of see that. So I'm going to vote against the ratio test. That doesn't look like something I'm eager to integrate. So I'm going to go with one of the two comparison tests. So if I just take this 1 away, I've got a version of the geometric series. So I'm going to compare it to eight to the n over 3 to the n, which can be written as 8 over 3 all to the n. This is a geometric series. A number to the n power. And the size of the number, the size of my multiplier r, is bigger than 1. So it diverges. Let's see, in the direct comparison test, our series has to be bigger than a divergent series. Is our series bigger than that one?
Yeah.
Yes, because it has less on the bottom. So I can use the direct comparison test. I can also use the limit comparison test. The direct comparison test says, since our series is bigger than a divergent series, our series diverges. If you did the limit comparison test and take the limit of this over that, the 8 to the n's will cancel, leaving you with a 3 to the n on top, a 3 to the n minus 1 on the bottom. So you're going to get a limit of 1. Any positive finite limit says they both do the same thing. So yet again, it says they diverge. Okay? I think the direct comparison would be the easiest thing outside of the test for divergence.
Will a geometric series diverge if R is 1?
Yes.
Okay.
Diverges if R is anything greater than or equal to 1. Converges only if R is strictly smaller than 1. Because really, a geometric series where R is equal to 1 means you're just adding the same number to itself over and over and over.
Yeah.
5 plus 5 plus 5 plus 5 plus 5. It'll keep it bigger. But there was one in webwork that had a funky limit.
I can't remember exactly.
Does anybody think they remember? Let me see if I can pull up
I think
webwork.
it was like 2 to the power of 2k, k factorial all over, I want to say k to the power of k.
That would be hard, wouldn't it? I'm gonna look it up though, because it was relatively difficult.
How did the basement work?
I heard that somebody tried to flush their calculus homework down the toilet and clogged it up, and it just kept running.
Lying.
I have my suspects.
It is simply 2 variables plus on the toilet.
Two things, items, that when they go to the toilet,
I really have no idea how it blended, but it did. Okay, I think 8.5 is the ratio test. I think you're right on that. I think you're right on that one. 2 to the 2k, k factorial, k to the k.
That sounded so close to just being right.
Okay, so let's talk about the ratio test. So in the ratio test, we take the limit as k goes to infinity of the k plus first term over the kth term. The ratio test always sounds better with music. And that was really good ratio test music. You know, not something ominous like dun dun dun. Okay, we take this limit and we get some number L. Now, when we have series that are not positive terms, you're going to see the ratio test in absolute value bars to take care of negative terms. And our definition of convergence in this case would be that it converges absolutely based on the absolute value bars. Okay, we get a number L. It converges if L is smaller than 1. Diverges for L bigger than 1. Inconclusive for L is equal to 1. So it works well when things cancel. So we're looking for factorials, products, and powers of n. Or of k or n, depending on how you want to write it, k's or n's. So this particular web work problem had it all.
Yeah, 4 questions to do it.
We've got 2 raised to the 2k power multiplied by k factorial divided by k raised to the k power. If that k factorial were not there, my choice of test would be the kth root test. But that's there. And I don't want to take a kth root of k factorial. So I'm going to try to test this for convergence using the ratio test. So our first step is to replace each k with k plus 1 and then divide it by that thing that we see. Oh, my camera. Let me get it out of your way a little bit. It might go off. delicate instrument. Let me see if I can see. That's even better. That was good that I moved it up. Got enough room for your legs?
What?
Got room? Got leg room? I want you to be comfortable. If not, we'll just make everybody behind you move. Okay, so when I replace k by k plus 1, this is going to be 2 times k plus 1. K plus 1 all factorial. K plus 1 down here. K plus 1 up there. Then when I divide by this, I can go ahead and flip and multiply over here. Like that. I am going to write this as 2 raised to the 2k times 2 raised to the 2 power. I'm going to write this as k plus 1 to the kth power times k plus 1 to the first power. Two to the 2k times 2 to the 2, k plus 1 factorial over k plus 1 to the k times k plus 1 to the first. And over here I have k to the k, 2 to the 2k, k factorial. So automatically we knock out the 2 to the 2k's. How does k factorial and k plus 1 factorial cancel?
Just get k plus 1.
Let's get the k plus 1. This is gone. Factorial is now gone. Right? K plus 1 factorial means k plus 1 times k factorial. So that just leaves me k plus 1. But that k plus 1 matches the k plus 1 on the bottom. So now I can cancel it. So I have that canceling with that. And I think that's all I can cancel. I'm going to have 4 times k to the k over k plus 1 to the k. That's a big old mess. I'm going to put these guys together and all to the k power. So if you look in the parentheses at the k divided by k plus 1, as k goes to infinity, the stuff in the parentheses goes to 1. But then I have a k power up here, so that's behaving like 1 raised to the infinity. Ooh, what do we do with 1 raised to the infinity? We have to use a logarithm. The problem, though, is the 4. Right? If I take the logarithm, I put a logarithm here and a logarithm there, and now I can't bring the power down. I've got the log of a product. Right? So I don't want to take the logarithm yet. I want to isolate the exponential term. Let's set the L over there. And now let's divide the 4 out. And say the limit of this is L over 4. I can't write right there, so I've got to erase. So I'm going to erase this stuff. So I'm going to say limit of k over k plus 1 to k power is equal to L divided by 4. Now I can take the natural log of both sides and be able to bring the power down. So I'm going to put a logarithm here and a logarithm there. And now bring the k down in front. K is going to infinity. The stuff in the parentheses is still going to 1. The natural log of 1 is 0. So this behaves like infinity times 0. What do I do about that? Put this down here on 1 over on the bottom. That's the easiest term to move. Now it has the right form for me to use L'Hopital's rule, because as k goes to infinity, I get the natural log of 1 is 0, 1 over infinity is 0. So now I can use L'Hopital's rule. Take the derivative of the top and divide it by the derivative of the bottom. On top, I take the derivative of the log of u by writing 1 over u times u prime. So 1 over u gives me a k plus 1 over k. U prime involves the quotient rule. So I take the bottom times the derivative of the top. Well, the derivative of the top is just 1. Minus the top times the derivative of the bottom. The derivative of the bottom is 1. All over the bottom squared. So there's the derivative of the natural log of k over k plus 1. Now I'm downstairs, I'm taking the derivative of 1 over k, and I get a negative 1 over k squared. All of that is equal to the natural log of the limit over 4. So I will try to simplify. How much I can do with this. And here, though, I can subtract the 2 k's and I get 1 over k plus 1 squared. And I'm going to divide by the negative 1 over k squared. Like that. One of the k plus 1s will cancel, one of the k's will cancel. That knocks out one of those. That knocks out one of those. So I got to take the limit as k goes to infinity of a minus k over k plus 1. We've gotten somewhere. Do you agree the limit on the left is negative 1? And now we're going to solve that for L. So we get rid of the logarithm with the exponential function. So we have e to the negative 1 is equal to L over 4. So L is 4 times e to the negative 1. Since we need to know how that compares in size to 1, I'm going to write that as L is 4 divided by e. Is that ratio bigger than 1 or smaller than 1? That is bigger than 1. E is 2.7-ish. So what's our conclusion on the ratio test? Divergence. divergence by the ratio test. Maybe you can do all of that again without looking at your notes. Why would it?
You know how it is. Put that on and say, no, that's not right.
You would get it. You would get it right. As
No.
a bonus? This is
Or
This is like web work problem 2.
Or not at all, or not at all. It could not be on there, and I will not lose any sleep.
I trust that you never lose any sleep. There's very little in there that was Cal 2. This was the Cal 2. This is what I did in my Calculus 1 class today when we were covering L'Hopital's rule. Didn't do that, and I don't want to scare them on the first day. I'll do it next time. I got to convince them first how cool L'Hopital's rule is before I whip out the big boys. So I take it you haven't gotten too far on this ratio test section? No? We need another wellness day?
Yes.
That's the best, yeah.
If you're offering.
Yeah, that's totally even for spring break. Totally even. 3 work days.
Okay, so perhaps I should work some stuff with the alternating series and with stuff in section 8.5. Yes, sir.
So I'm confused with alternating series. Is an alternating series alternating like convergence? No, conditional convergence? That's what I'm confused on. Is conditional convergence only conditional if one converges and one diverges?
Yes.
Okay, because I thought that I like, oh, the absolute value had to be convergent.
Nope. I can give you examples. So let me write down what I just said. Unless you got it. Okay, so that's stuff that's in section 8.6. Does that sound right? So, in section 8.6, a series is said to be absolutely convergent if it converges an absolute value by some positive term series test. Our positive term series test was the is it P series? Is it geometric series? Can we integrate it? Direct comparison, limit comparison, a ratio test, or root test. If it converges an absolute value, then it's absolutely convergent. If it doesn't converge an absolute value, it might converge if we leave the negative stuff on it. If a series is not absolutely convergent, it might converge without the absolute value signs on it. In other words, you leave the negative terms intact. Right now, the only test we have for series with negative terms is the alternating series test. So for instance, now we would run the alternating series test. So if it's an alternating series test, we try the alternating series test. What are the 2 things you look for in the alternating series test?
The limit approaching 0, the derivative is negative, or is greater than k plus 1.
Right, decreasing limit to 0. We want to know, is it decreasing? We want to know the limit of the non-alternating part is 0. That's the alternating series test. If it does both of those, if these hold, then the series is conditionally convergent. If it's not absolutely convergent and not conditionally convergent, it's just a big old divergent series. But if it's absolutely convergent, then it's automatically conditionally convergent. Absolute convergence implies conditional convergence, but conditional convergence does not imply absolute convergence. Okay? So you check absolute convergence first, conditional convergence. If this is no, if it's yes, you're done. Absolute convergence implies conditional convergence. If it's conditionally convergent, then you're done. You just say it's conditionally convergent. If it's not conditionally convergent, then it's divergent. So here's an example. Say the cosine of pi over k. Let's just make it pi times k. What is pi over k crapola? Over k squared. This is an example of a series that has some negative terms, but it's not an alternating series. For some values until k is equal to a half, the numerator is going to be a positive number. Once k is a half, until k is equal to a 1, the numerator is a negative number. And then when k is 1, I got 0. When k is 2, I have, when k is 1, I have negative 1. When k is 2, I have 1. Well, it does alternate, doesn't it? Okay, so it alternates. I should have put it on the bottom. But it alternates back and forth. The numerator goes back and forth between 1 and negative 1, depending on what k is. But if we check for absolute convergence, I'm going to run a test on this series. K squared is already positive, so I'm really just taking the absolute value of the numerator. But I said depending on whether k was even or odd, the numerator is 1 or negative 1. So a comparison test falls into my lap. At its very largest, the numerator is 1. Right? I should write that separately. I should write that the cosine of pi times k over k squared is less than or equal to 1 over k squared. So I'm going to compare to the series 1 over k squared. Tell me everything you know about the series 1 over k squared.
Convergent P-series.
Convergent p-series. So this is the statement that the series I'm testing is smaller than a convergent series. That's the direct comparison test. Smaller than convergent is convergent. So it converges in absolute value. This is absolutely convergent. So I don't have to check for conditional convergence. That means if I take the absolute value bars off of it, that series itself converges. It converges in absolute value. It converges without absolute value. Okay? All right, here's one. -1 to the k plus 1 divided by the square root of k plus 4. The instructions, unwritten ones, are, is this series absolutely convergent, conditionally convergent, or divergent? So I'll write it. So we make a quick test to see if it's absolutely convergent. If you put that in absolute value bars, all you lose is the numerator. It becomes a positive 1. We'll take a quick guess at what the series 1 over the square root of k plus 4 does.
Divergence,
And how can you prove that to me?
P-series, or
It's
comparison.
almost a p-series. You can compare it to a p-series. You have to do a limit comparison test. You can do a limit comparison test with a p-series. Another test that pops to my mind is the integral test. That's easy to integrate as a 1 over u to the 1/2 du. Right? Either one's going to give you the same result. This is going to be a divergent series. Let's do the comparison test. This is a divergent p-series. I can't do a direct comparison because the p-series that I picked has less terms in the bottom. So the given series is smaller than divergent. That goes the wrong way. So I've got to do the limit comparison test, where we take the limit as k goes to infinity of the given series over the series that was the lookalike one. Any positive finite limit means they both do the same thing. So I take 1 over the square root of k plus 4. I divide it by that one. But when I divide it by that one ends up here. Divide 1 over square root of k plus 4 by 1 over the square root of k. The flip and multiply step gives me the square root of k on top. And now the same power is on top as it is on the bottom. So that has a limit of 1. Any positive finite limit means they both do the same. That means this series in absolute value bars does not converge. So I'm going to say it's not absolutely convergent. It is an alternating series though, so we're going to check the two tests, 2 parts of the alternating series. So we got the no, now we're going to see if it's conditionally convergent with the alternating series test. Not absolutely convergent. Next, check for conditional convergence. The alternating series test. So the quick part is to see that the limit does go to 0 of the non-alternating part. It's quick to show it's decreasing just by comparing that term to the k plus first term, since the k's only appear in the denominator. If I had k's in the numerator and the denominator, I'd show that the derivative was negative. But I know that k plus 4 itself is smaller than k plus 1 plus 4, or k plus 5. Those are both positive numbers, so I know the square roots behave in that same way. And then if I flip both sides, it flips the inequality. Which says the term in front is bigger than the term right behind it, so I have a decreasing sequence. So that was the second step, to check if it's decreasing. So it satisfied the 2 steps of the alternating series test. My conclusion is that this series is conditionally convergent. This lent itself well to a comparison test, but if I had factorials, products, powers of k, I have a general ratio test, where the ratio test is done in absolute value with the same conclusions, and a general root test, where the root is done in absolute value. So let's look at something like that. Let's see if I have any. Okay, so same. Is this absolutely convergent, conditionally convergent, or divergent? And let's take our series to be minus e to the n over n factorial. The minus sign in front of the e acts as a coefficient of -1. So you can rewrite the numerator as -1 to the n times e to the n over n factorial. And that makes it an alternating series. But I'm going to check for absolute convergence first with the general ratio test. Using the n this time. If I take -1 to the n and increase the n by n plus 1, it's going to cancel with the -1 to the n anyway. So these absolute value bars will get rid of the -1 to the n. So I'm not going to use it. I'm going to write my an plus 1 as e to the n plus 1 over n plus 1 factorial, and then I'll put my an in there. I don't need the bars, but I'm going to put them on there because these are all positive. Then I'll have an n factorial up here and an e to the n down there. Cancel what cancels and tell me what's left. E to the 1 divided by
N plus 1.
n plus 1. Right, the n factorial cancels the n factorial that's behind the n plus 1. The e to the n cancels the e to the n. Here leaves me e to the 1. Well, what's that limit right there?
0.
Because e is a constant, n's on the bottom. Limit is 0. If the limit is smaller than 1 and everything's an absolute value, the series is absolutely convergent. Okay? An example of a series that's not absolutely convergent and not conditionally convergent, just tip that series upside down. Have n factorial over minus e to the n.
What did you do to the -1?
Take the absolute value of it, right?
Oh, right.
If you want to put it in there, I'd have a -1 to the n plus 1 up here, and down here I'd have a -1 to the n in absolute value, so that cancels, leaves me -1. Eventually I'm going to take the absolute value of it.
Okay, I got you.
So I just blew it off right off the chart. Don't want to waste valuable chalk. Okay, and what else do I need to tell you? Does it seem like about it? Let's do this one, because I want to show you the nth root test. Same instructions. Absolutely convergent, conditionally convergent, or divergent. So that -8 to the n, again, x is an alternating series. You can think of the numerator as -1 times 8 times n, which is -1 to the n, 8 to the n to the n. Instead of using the ratio test, though, I notice everything in here has a power of n. So I'm going to use the general root test. The general root test says that if I take the nth root of the absolute value of an and get a limit as n goes to infinity equal to some number L, then for L smaller than 1, it's absolutely convergent. For L bigger than 1, it's not absolutely convergent. So you need to check for conditional convergence. If L is equal to 1, you need to try something else. It's inconclusive. And so when I put that in absolute value bars and take the nth root of it, Then I can take the nth root here, put the absolute value bars back on the minus 8n, take the nth root there. Well, taking the nth root of something to the nth power just leaves me the expression as the base. It left me at n to the 6 because an nth root means a 1 over n power. So if I have n to the 6n raised to the 1 over n, you multiply exponents, and you have 6n over n, which just leaves us n to the 6. Is that okay? Now I take the limit as n goes to infinity, and what do you get?
0.
That's smaller than 1, so this series is absolutely convergent. Okay?
Can you real quick repeat how you got from, like the limit is n approaches infinity a n?
All right, let me put that one extra step in. It's going to be the limit as n goes to infinity of the absolute value of negative 8n all to the n over n to the 6n, and now I'm raising that all to the 1 over n. And that's the nth root. And when you raise a power to a power, you multiply exponents. So that leaves you a negative 8n, which is just 8n, or 8 times the absolute value of n. N's positive since it goes from 1 to infinity. So it's just 8n over n to the 6th. You can cancel the n's and get 8 over n to the 5th, and that's limit is 0. Okay? Now, if you remember that expression that we had before, where I did all that stuff with the logarithm, I ended up with those n powers after I'd done the ratio test. So I can't just whip out the root test in the middle of the ratio test. So even though you see n powers at a certain step, doesn't mean this applies. This has to come at the beginning. Okay. Better? So what are your thoughts on this web word problem? Same instructions. Let's take n plus 7 to the nth power. And down here, 4 to the n squared. Absolutely convergent, conditionally convergent, or divergent. Well, it's a positive term series, so whatever conclusion you get from it means it's absolutely convergent. It can't be conditionally convergent because there ain't anything in here that's negative. What do you want to try? Nth root test. I got an nth power upstairs, nth power downstairs. So tell me what the nth root of this looks like. N plus 7 over 4 to the n. Again, an nth root means I'm multiplying each of these exponents by 1 over n. So that leaves me an nth power here. What's that limit going to be?
0.
Good. It's absolutely convergent. Okay? Super. All right, so on Friday, see if you can put all your tests together. I've got a handout on Blackboard if you want to print it, and we'll work on it in class. You'll work on it. You're not going to watch me. I'm going to walk around and watch you. Okay? So print out the list of positive term tests so that you can look them up and see which test you want to use. And I want to make sure you write things up neatly and in an organized manner the the way I want to see them on the test. So it's going to be kind of practice the way I want you to write things up. Okay? Again, getting the right answer isn't the objective. Explaining how to get to the right answer is the objective. Good? Wait on. You guys at home okay? You guys at home? Any questions from anybody at home?
I got one question.
Yes.
So if you're trying to solve the sum of 1 over like k to a power of natural log of k, like where the natural log is on the bottom.
You have
I looked at it now.
natural log of k here,
Natural log in the denominator.
the denominator, and a k to a power here,
K to the power also in the
k to the power also in the denominator.
denominator.
And you want to know what test to use?
Yeah, because I tried using q log, I couldn't.
It's not a q log, because q log has to have the log on top, and k to the q on the bottom.
Right.
So here I would use a comparison test. I know the log of k is always smaller than the square root of k. So I would say that this is smaller than 1 over k square root of k.
Oh, okay, I got it. All right. And since
Actually,
that's
it's bigger, right? Because I put this is bigger than that,
Oh, right.
right?
Oh, and then
Because-
you do a limit.
And then do a limit comparison test.
Okay, I got it, thank you. So whenever it comes to that, you just transform the natural log of k. to
Natural log of k is down at the bottom of the food chain, right?
Yeah.
So
Okay,
I
I
would just
got
pick
it.
the guy bigger than it on the tower of power and compare it.
All right, thank you, that makes sense.
Okay.
All right, Keith.
I was wondering if you had the homework.
I do, probably, maybe not.
I'm really curious to see if I screwed up on that, now that you mentioned at the beginning of that class. So we don't know what we're doing.
Oh, I did catch you something here. I did. Let me take a look at that. Oh, gosh, I forgot to give everybody's back. Let me see what I-
Six.
Because you were close. Let me see what I said you did wrong. Oh, you said it was a geometric series, but it's not a geometric series. It's compared to a geometric series.
Oh,
Once you put that 3 down there, it's no longer geometric.
that one.
But you can compare it to a geometric series.
Right, with the
And
direct
you were able to
comparison
do a
test.
direct comparison. Either direct comparison or limit comparison.
Oh, boy. To be honest, Leo, I kind of rushed that one, so.
Well, that's what I mean. Everybody's making little tiny mistakes like that. And that's why I want to catch them before they grow into big mistakes.
Hopefully, I'll remember that the next time. I think I just completely keep on confusing my geometric